I am indeed. I'm very excited to present to you our friend and colleague, Karen Daniel. She comes to us all the way from North Carolina State University remotely. Um, and she is a professor of physics, but she had an interesting trajectory. She started her undergraduate degree at Dartmouth College, and then she taught.
Whoops, I don't hear anything suddenly.
David,
Yeah.
did you mute me?
I did not mute you, no.
Okay.
Did anybody hear anything of what I said?
Just that Karen comes from North Carolina, Carolina State University.
Excellent. This is all going to plan. So I will start again. We're excited to have Karen, and I wanted to start with a little anecdote, which is that she not only went to, but also taught at St. Anne's.
I did not go there. I only taught there.
Didn't go there. You only taught there. Okay. The New York school that some of you might know of in Brooklyn. It's an all-girls school, isn't it?
It is not.
It is not. Okay, I thought that it was, but lots of famous women come from there, so that's probably why I associated it. Okay, so after teaching physics for a little while in the school for a few years, then she went on to do a PhD in physics at Cornell University. And after her doctorate, she moved to North Carolina, and she did research at Duke with our colleague Bob Berenger, who is unfortunately not with us any longer. But she is keeping the spirit alive for sure. Even in this seminar, I can see from the title slides. After having done her postdoc at Duke, she then moved to North Carolina State University. And since then, she's been studying all kinds of interesting granular phenomena, from the flow to the piles of sand to fracturing in gels. And she has received the Alexander von Humboldt Fellowship, with which she did research in Göttingen in Germany. And she's an APS fellow, and she has collaborated with a number of us in the past years. So we're excited to hear what her new research on, and now let me see, bending, slipping, and breaking is all about. So welcome, Karen.
All right, thank you. This is lovely that to have me virtually. I just want to check that I think I fixed the settings. Now you should just see my screen and no other mess. Is that correct?
Although your slides are cut off a bit. At the bottom.
At the bottom. Well, you know, let's go with, how about that? Is that any better?
No different. Did you try AutoFit?
Maybe try zooming out a little.
How about that?
Yes.
That is good. Except
all right,
now,
we will.
yes.
Now what?
Good.
All right, we'll go with this. All right. So yeah, as Yasna said, I'm actually a native New Yorker. I've been in North Carolina for almost 2 decades now. But I still maintain some close enough ties to the city that I follow the New Yorker's caption contest every week. And this week's contest is essentially the topic that I want to talk about today. So this would be a losing entry. It is not funny. And so my challenge to you is to, at the close of this contest, the close of this talk, find a better caption to submit than what I have submitted, which is just to ask, is this staircase rigid? So this is me very literally saying what I would be saying if I were the woman there at the bottom of the staircase. So the topic of today, what we're talking about today, is rigidity. And I just want to, think about, I mean, we probably know what we mean by it, but let's pretend we want to think about it some more. So, rigidity is just the ability of a system, to resist stresses. Yasna raised her hand.
I just wanted to propose that maybe people place their ideas in the chat if they wish, and we can review them right at the end or in the after party.
Yeah, and I would also say that if you're someone who wants to ask a question but don't have like a microphone video situation lets you ask it, just ask it in the chat, and then maybe I'm actually happy to be interrupted by questions, but I can't really, with my current setup, monitor what you're doing or you're typing in the chat.
David and I can.
You can just let me know. Yeah.
If there's somebody.
Excellent. Yeah. So, the ability of a system to resist imposed stresses, and this actually, oh, it's sad this little GIF isn't playing but in any case, I will describe what it does. So, if you have some material, and this is sort of a truss network, the left side of this is nicely rigid, but the right side is not. And if you were to slide one of the purple beams over to be in the other square, then both sides would be rigid, even though they have the same amount of beams and same amount of junctions, right? So materials, and this is just a very simple example, often have both rigid and floppy subregions within them, right? And yet we often take system-wide averages, right? So where are those useful and where aren't they? And if something is rigid, and it does fail eventually, where those failures are going to occur with respect to where these rigid and floppy regions might be, or the degree of connectivity, or other things like that, and what sets that criteria, right? So this is a fairly broad set of questions, and I'm not going to answer all of these, but I'm going to talk about things that we've done that get us towards understanding at least what some constraints on those might be. Okay, and if you're talking about a granular material, which is what I often talk about, there's some things that we all sort of know already, which is if you're at the beach, it's easier to dig at the top and it's harder to dig at the bottom. So what's different about the sand at the top than at the sand at the bottom, right? This is the same if you're building a structure, right? That there are spatial gradients sometimes in these things. And so we want to be able to look inside and see what's going on. Okay, so today I'm going to talk to you, it's going to be a little bit, a lot of material in a short amount of time, because it seems to me that neither one framework nor one system serves to totally answer the question. So I'm going to talk about 3 different frameworks, and they sort of span from having very little physics in them to having a lot more physics in them. And I'm actually going to not just talk about grains. I'm going to talk about both idealized granular materials and also some disordered lattices. And I'll tell you a bit why that's the case as we get to it. So the 3 frameworks we're going to use are, one, just simple network science models where it's almost just topology. Who is connected to whom, right? Who is in physical contact with whom? If you add a little more physics, it's sort of the introductory physics problem of what is force and torque balance, and do you have enough constraints to satisfy your degrees of freedom or not? And if you want to get up to a little bit more physics, talking about vibrational modes in a fully connected system, right? And the picture at the upper right is I'll play it again. It looks like I don't have the controls to play it again. Okay, so it was moving before, and we'll see this movie again. So I'm going to use a set of 2-dimensional system composed of grains, and what you can see, the bright stripes through there are where the forces are. I'll talk a little bit more of that down the road. And what we found is that, in fact, inspired by Michelle Driscoll's work, who many of you know from NYU when she was at NYU, also starting to think about lattices that are disordered and are very similar to the kinds of same sort of patterns we see in the grains, but are a different physical system. Okay, and that's really helpful us for answering some questions. They're easier in the second system than the first system. Okay, so this is a little movie of a bunch of grains sitting inside that yellow region where the inner wheel is spinning, and it's actually not spinning, it's stationary. You can see the inner wheel at the bottom. Okay, and it's ramping up the torque. So as it ramps up the torque, you're not seeing a large drama in the grains yet. You've seen some rearrangements of the forces. Every place is bright, there's force. Okay, and at some point, the torque gets too high, it can no longer resist the stresses, and everybody goes ahead and rearranges, and it fails. Okay, so it was rigid for a while, and eventually it was no longer rigid. Okay, and so this is the kind of process that goes on, quite commonly, out in the real world. Again, to go back to the beach sand example, how hard can you step before your foot slips? To much more geotechnical examples of whether or not embankments are going to fail, whether or not an earthquake is going to destabilize something, and so forth. Right. So,
Karen, can I ask a
please do, yeah.
So how are you visualizing the forces here?
All right, so how about this? Next slide. So how I'm visualizing the forces. So we use a trick. And so this is the reason I work on two-dimensional systems and not on three-dimensional systems. And that is I want to be able to see the forces. And the trick is this, is that most polymers are birefringent. So they rotate the polarization of light if they're under stress. And so if you take a polymer disk and you view it between a left circular polarizer and a right circular polarizer, normally light would not be able to get through that configuration. Okay, that's the low stress picture here on the left. And if you impose some forces, so a medium picture, we've imposed some compression on this 5 disks. The birefringence of the disk causes the light to be rotated ever so slightly. Okay, and now even though the left circularly polarized light shouldn't have been able to get through the right circularly polarized film, some of it is able to get through. Okay, and that's where you see bright. Okay, however, if you push even harder, now some of the light has gone around too far and now it can't get through again. Okay, so you start to see a series of fringes. Okay, and this is very well developed. I'm proud to say late 19th century, early 20th century science. It in fact was often used as a technique for finite element modeling before we had the advent of computers, as one of a really nice way to see stresses during engineering design processes. And for us, it allows us to basically turn every grain in our system into a SPI particle. So it reports to us what its degree of stress is. Okay, and so what you were seeing in this movie, the page before, okay, is that every place is bright is a place that has a load is being supported on that grain. Okay, and you'll be able to see slight shifts in those particles, brightnesses, as the load redistributes. And the particles have hardly moved at all, okay, and yet the load is able to redistribute through here, right? So there can be stable configurations of grains that have different sets of configurations of forces, okay? And at some point, the system is no longer rigid, okay? The load has become too large, okay? And in fact, there is a rearrangement of both the grains and the forces. So this is the main technique that we're going to be using in a bunch of places throughout the talk. And one of the nice things is this is not by no means the only way to see these sort of chains of forces that I just showed you. They've been seen in lots of other systems. The lower left is some of Yasna's own work. So in all sorts of particulate systems, whether they're colloids or emulsions or gel beads, this is something that, there are a number of different techniques. None of these were done with photoelasticity. They were done with other techniques. But these sort of chain-like structures through which forces are transmitted have been the focus of a ton of work because they seem to be the backbone by which forces are supported, right? And therefore give rise to rigidity. And I'll tell you now that part of what I'm going to talk about today is to say that the backbone as you see it from just the bright particles isn't the full story, right? There are some actually collective effects that you need to take into account to really better understand what's going on. Okay. The other thing that I think is intriguing about this set of images is that somewhere along the way, we seem to have decided that bright force chains are red. And that is not something that I have done in my pictures, okay? But if it helps you to think of that, please go for it. All right. And so these force chains have long been known to be important, right? And so a really nice paper that is beloved to me, that was done in Bob Berenger's lab by Piyush Majumdar, who's also at NYU now in the mass department. You can see things in these patterns of forces. And again, bright is larger force that make it very clear that these two samples were exposed to a different stress history. In one case, it was compression, in the other case, it was shear, and the patterns look extremely different. Okay, and so lots and lots of information has been learned from this technique over a large number of years. And one of the nice things about this technique is that it's not a simulation. These are not geotechnical grains. These are not what an earth scientist would call a rough particle that can break. They don't have the same high stiffness that geologic materials do, but they at least are real. Okay, and they have some features that I want to highlight that they're slightly different than how we necessarily think about simulations. Okay, so one is that the particles are actually rough. Okay, if you zoom in on the edge of the particle, of one of these particles, like I've done in the upper left, I've highlighted with a blue line. Our particles have sort of an asphericity at the level of 10% and a roughness of about half that. Okay. If you take a look at the picture I already showed earlier, where the particles are just being compressed, you can see that there's actually flat regions between the particles. The particles have deformed elastically. They don't stay circles, right? And if we try to measure, these are dissipative from friction between the contacts and also from inelasticity, right? And they don't necessarily have mu equals constant. In simulations, people often assume that to be the case. This is from some measurements we did recently where we were trying to determine what our friction coefficient was. And we did it many, many times. Some of these particles were close to the Coulomb threshold, some were not, presumably, and we see a whole range of values. We don't see a single well-defined value. Okay, so these are not the idealized particles that people show in simulations. Okay, and if you do the same experiment over and over again, right, you have you don't get the same answer, right? These are not perfect. So this is I'm going to say movie in quotes because it's actually just a bunch of still images from my former postdoc Jonathan Kolmer, now in Duisburg in Germany. He made the same configuration over and over, and it's never quite the same. Okay. And this is due to the history of frictional loading. It's due to different disparities, right? And this is sensitivity to initial conditions, even if they were perfect, right? So there's a lot of richness in these systems, even though they seem fairly simple. Okay, so I'm going to tell you now about a couple of different stories of things we've learned from using descriptions of these systems at various levels of complexity reduction. Okay, and one of the ways to sort of throw out almost everything interesting and keep only one, sort of two pieces of information is to say you have a packing of particles. You say that each particle is a node in a network or a graph, depending on your language. Any two particles that are in contact, you draw an edge between. Okay, and you can decide, based on what you're interested in, to either say you're going to keep weights on those edges, for instance, the strength of the force on them, since we do measure the forces, or just to say that they're connected, right? And so these are called adjacency matrices. And so the letter E is a binary adjacency matrix. If you imagine that there's a list of particle names down the left and a little list of particle names across the top, you would say that Sally is connected to George, right? Or you could say Sally is connected to George with a stronger or weaker weight. Okay, and so once you have this written as a mathematical object, it's just a matrix. You can tap into a whole host of tools that mathematicians, applied mathematicians, and social scientists, and everyone under this, people working on neuroscience, have developed mathematical tools for working with these objects. Okay, and so this is for I guess almost a decade now, I've been working with Danny Bassett and Mason Porter. And we've explored a whole bunch of different network metrics for looking at, trying to answer problems in granular materials. And this is sort of just a summary of the kinds of things. There are dozens, if not hundreds, of different network science methods. And I'm just going to give you a quick overview here, depending on what problems you might be interested in. If you're interested in system scale questions, right? Averages, properties of the system. So, for instance, global efficiency. How overall, how connected is everything, right? Do you want to look for domains of well-connected particles that are a subset of the whole system? Notions of modularity, right? Are you looking for paths of transmission, right? Do you want to extract the most commonly used paths of connectivity, right? These are commonly called the betweenness type measure, right? They might tell you where there are bottlenecks in the system, right? Or are you interested down at the particle, the node scale for single particles? What's the cluster that some particle is adjacent to? Who is it just neighboringly connected to? So depending on what you're interested in, there's a whole set of techniques out there that are really good for answering questions, and they only require that you have a list of who is connected to whom in order to use them. Again, possibly with weighting information. So I'll just give you a sample of what you can learn for these from these types of measures. Okay, and the one I'm going to tell you about is a property called Betweenness Centrality. And the analogy I'm going to make, this which is one that is useless in the time of COVID. I'd usually make this analogy that the red node here is Chicago O'Hare. If you want to get from New York to LA, any place on the East Coast to any place on the West Coast, you're gonna probably have to go through O'Hare. Maybe you'll need to go through Texas, right? So you can identify that airport as being central because in order to get from a random airport to any other random airport, there's a high probability that the shortest path would take you through that airport. Okay, and so the toolbox we use is one from the Brain Connectivity Toolbox. It's an open source set of codes in MATLAB that will calculate this for any network that we give it. Okay, and again, this can either be weighted or not, depending on what you're interested in. So if we do that for that movie that I showed you of the sort of random regeneration of the same picture and over again, that I showed you a couple frames back, okay, and we say, all right, which particles are going to be on the force chains, right? So if I do that over and over again, what's the probability that a particular particle will end up on a force chain, right, or not? And what you'll notice, let me just go back to that movie, is that there are some particles in here that seem to always be on the force chain, right? And some particles that seem to rarely be on one of the stronger forces. Okay, so they're not all the same. They're not as likely or unlikely to be on a force chain. It seems to depend on something that we can't see. Okay, and I'm going to make the case that just knowing the topology can predict that. Okay, so if I calculate this betweenness quantity and then I normalize it, don't worry too much about that. That's the horizontal axis, and I calculate for repeated experiments what the mean pressure is on that particle, okay? And we have means of actually turning these photoelastic measurements into vector force measurements. And then we can turn that into a pressure. And then I'm gonna bin my data. So there's a purple bin, a yellow bin, an orange bin, and a blue bin from high to low. And I'm gonna look at histograms of those bins. So if you're in the purple bin, you end up in the purple histogram. If you're in the yellow bin, you end up in the yellow histogram. If you're in the orange band, you end up in the orange histogram. And these look quite different from each other. They're approximately exponential, so they're well characterized by a mean. And if I plot what that characteristic betweenness value was, so the slope on a log ln plot, and versus which force bin in, you can see that the higher the betweenness of the particle, okay, the more likely it is to be in a high force bin. Okay, and so there is randomness in this process, right? Every time we generate the network, it's slightly different, okay? But there is a trend, okay, that if you are on many paths, then you're more likely to end up with lots of force, okay? And if you think about the mechanics of bringing two walls in towards each other and particles gradually coming into contact, the more possibilities there are, the more likely you end up with a force. Okay, so this is a very probabilistic argument, right? Not a very mechanistic argument. Okay, so that's an example of how you might use one of these network measures. Okay, so here's a question I would love to know the answer to. And I'm going to tell you right now that I'm not going to tell you the answer to it. So for instance, could I use that measure I just described or one of these other network measures to forecast the failure locations? And I'm going to say right now that we have failed in this task so far. We got started on it and it was hard. The graph I'm showing on the left is one of our attempts to correlate things. And so we actually stopped working with grains for a little while, right? We said, this was a really hard project. We couldn't tell what a failure was. Things weren't repeatable. And so we actually cheated. And this was, like I said, inspired by some of Michelle Driscoll's PhD work. We said, what if we just take our picture of the force chains, write the contact network, and then just cut that out as a plastic lattice, right? And then try to break that instead. So this was the work of former postdoc Estelle Berthier. So she took data from the granular experiment, simplified it to just be a lattice. She could then make multiple of these and less material disorder, although there is still some material disorder, and do experiments on where those would fail. Okay, and so that's what I'm going to tell you about now is a little diversion off the granular problem. Okay, so one of the things we learned is if we calculate that betweenness value, and so the yellow here, yellow is high betweenness, and it gets recalculated every step. Okay, and at every step that we compress it, the red circle is a place that the lattice broke. Okay, so this is a very distributed failure, right? So we're slowly compressing the lattice and it's breaking in various places. It'll just run again in a second. Okay, let me just run that again from the top. Okay, and so what we see is that, first of all, the yellow stuff that's on here is changing because every time you make a break, you break a spot in the lattice, you have to recalculate the betweenness, right? So this is but at every step of the way, if you take all of them together, about 3/4 of the time, any of the edges that failed are larger than the mean, okay? And most edges are not larger than the mean, right? So only about 1/3 of the edges are larger than the mean, right? So there is a increased probability of failing if you're on one of these high betweenness paths. And again, you can think of these as the airline hubs. If you want to connect random nodes to random nodes, these are the ones that are on the most shortest paths, and they are the ones that are most likely to break. Okay, and again, this is just the topology. There is essentially no physics in this, right? It is just topology, network topology. Okay, and it does a remarkably good job. Okay, now our goal here, if we want to do something a little bit better, can we do better? Yes. Okay, so one of the things so the plot I just showed you, a nice way that sort of people look at failure is, you know, how many guesses could you have made? That's the possibilities, to how often were you correct, right? And so if you have a perfect test, that's the red line, this outer bound. You can't ever reach that. The blue diagonal is random guessing, not very good. And so what I just showed you with just using centrality is the green line, and it does better than random guessing, okay, but not as good as a perfect prediction, okay. If we adjust it slightly and we basically make the top and bottom where we're compressing it basically super particles that are connected to all the ones that touch it, we actually can improve that slightly. That's the yellow. So the yellow still just has topology information, just including the walls as part of the topology. And people, of course, have studied fracture for a long time. You can go into the literature and ask, you know, who's been doing that and how do they predict it? So a common model people use is what's called the fuse model. It maps onto this problem. You can say each beam is a fuse and the loading is like a voltage. And at some point, if you cross some load, i.e. you cross some current, the fuse blows and then the current has to get redirected to other paths, right? So if you make that analogy, and you predict where things are going to fail, that's actually the blue lines, just they're very close to the yellow lines, right? So this fuse model has a notion of a failure criteria and having to resist a load, and it doesn't do that much better than just topology alone. Okay, you have to actually really go put in the physics that you have actual beams that have actual moments that support stress, and then you can start to get something much closer to the perfect test. Okay, but you don't need a lot of physics to do pretty well. And that is, I think, a message for a lot of cases where, you know, if we're doing experiments on soft matter systems, you know, we often know how things are connected, but we don't know the weights of the forces between them, right? We don't know the strengths of the connections, right? And so this says, you know, even with very reduced models, you can do a lot.
Karen?
Yeah.
Sorry, just a pro forma thing. People are having trouble seeing the titles because of the zoom bar. Is there some way to move that out of the way?
I will keep an eye on where it is, and I'll just keep moving it around.
Bueno.
Good. I forgot that you guys would be seeing that too. Yep. All right. Again, apologies since this is not my usual Zoom setup. I don't have everything totally figured out. All right. Okay, so let's look at some of this. Here's a bigger movie of what's going on there. So this is just continuous cross-stochastic sheets. They've been cut in a laser cutter. It's being compressed in an instron. You can start to see the top pushing in there as it comes to the end. And this movie has had the failures overlaid on it, you know, as they break, right? And so what you can see here is that it looks like the breaks are just happening all over the place, right? This is not making a nice clean fracture, right? But that's because of the particular lattice I decided to show you. Okay. So one of the things that we can do is go to our granular experiments that were done under, like I said, this arose because we tried it in granular materials and hadn't done so well. So we switched to using lattices. And we can go look for experiments that had a low average coordination number. So I'm showing a 2.4 up to a high average coordination number, which is 3.6. And if you aren't familiar with the idea of a coordination number, there's a little zoom in here. So if you just have one edge coming in and one going out, that's a coordination number of 2. If you've got 3 edges coming in and out, that's 3. And z equals 4 is when you have 4 edges coming in and out, right? So there's a mix of these throughout the whole system, and it's a well-defined average. So we have a whole set of these that we've made and done experiments on, okay? And the one I just showed, the first movie I showed you was all the way to the left. It was a bunch of failures happening all over the plastic, okay? And so an engineer would call this ductile-like. There's a broad distribution, distributed failure. It's a bit of an ooze. Right? And as you can see, as you increase the connectivity, we get more and more crack-like behavior, right? So this is what an engineer would call brittle, okay? And you see distinct cracks where things fail along well-defined paths, okay? And so what I've drawn on here is some ellipses that sort of encompass most of the failures, and there's a length to width ratio on those ellipses, right? And so the length to on the left, where it's very ductile-like, the ellipses are very round. And as you go towards the right, the ellipses are much more elongated, right? So this is a morphological characteristic that you can use to describe your cracks.
Excuse me, Karen, just a quick question. Are all of these different structures derived from observations of packings, or have they moved over now to becoming completely sort of synthetic structures?
So one of these is synthetic. So one of them is a cheat where we added we randomly added some extra links in to fill out our distribution. I think that might be the 2.6. I can't remember for certain. But these are all taken out of granular data. And actually, you can see that some of them come from the same run, like number 3.0 and 3.6. You can see some of the same structures in. Right, so those actually came from early and late stages of a single granular compression experiment. So these are all so this question is extremely interesting for another reason that probably I'm not going to talk more about. So I'm just going to say it right now. We actually tried to generate synthetic networks, and we went down a giant and fascinating rabbit hole that you will not be surprised. You know, the kind of randomness you put into your random network gave us very different behaviors. And so in the end, we decided to just stick with ones that all had the same origin. And so whatever the randomness you get from granular packings is, that is the kind of randomness we have here. And so these are the same kind of randomness. And controlling for that turned out to be very important. All right, so here's this, this sort of ductile to brittle-like failure. Okay, so I'm going to look at ones where we have the ductile-like failure first. So this is what a typical low connectivity response happens. So initially, I'm calling that phase 1. There's an elastic response, right? So it's not perfectly elastic. This is not perfectly linear. It's not linearly elastic. Okay, but as you compress by some amount delta, the force rises and the system compresses. This has 2 different kinds of response inside of it. The beams will bend, right? So they will both stretch and bend in order to accommodate the load. Okay, and this will actually cause the intersections to rotate. Okay, so there's a huge, rich array of stresses put on this poor little plastic. Lots is going on to it. Okay, and at some point, one of them will fail. Okay, and at this low coordination number, that failure is progressive, right? So once it fails, it doesn't heal, and it's highly distributed. And each one of those failures, you can see, is associated with a drop in the force. Okay, but this is it fails, and then it loads again, and then it fails, and then it loads again, and then it fails, right? So this looks a lot like, for the granular folks, stick-slipped behavior. Okay, well, that's a different effect. Okay, and so this results in a spanning crack eventually. So this crack didn't form in one clean break. Okay, but in the end, it did actually fail all the way across the material by some random process. Okay, so if we compare this to what happens, so that green line I just showed you, which looked huge, is now the very little bitty green line on here. Okay, so that was the low Z green example. Okay, if we start going through our examples of larger and larger Z, what we see now is that we have much more catastrophic like failure. And in fact, this orange one at the right loaded up, failed once, and then loaded up again and failed along the other crack. So the whole cracking process took place in 2 steps and 2 steps only. Crack and then crack. Okay, so this is very brittle-like. Okay, and in between, you can see from the graph, you see a combination of those 2 behaviors. Sometimes you get a nice crack, sometimes you get distributed failure. Okay, and this is being tuned by the degree of connectivity. Okay, so we characterize that a couple different ways. So one is that we, as I mentioned, that looking at the ratio of the crack, how wide the crack is, we have a measure for that. Okay, that's the purple line. We also have a measure for what the load at failure is. These have been normalized. Don't worry about how I've normalized them. They both follow the same trend, right? That and so we can use this to classify things as being either brittle-like or ductile-like. And in fact, there's a whole continuum of behaviors between that. All right, so with that,
Karen,
yes.
Karen, how do you vary Z in the packing?
So actually, this movie here will tell you that. So I'm going to show this movie, and then I'll go back to the introduction to this movie. So this is what the experiments looked like that data came from. And let me just play it again. And what you can see is the walls are moving, and the load is changing. And so we just actually carefully farmed old data. So this data set might not have been one that we used, right? But we went through our whole library of lots and lots of data we had sitting around of granular packings on the Airtable and just farmed ones that had different Z's and then threw away the information about the force weights. Yeah, so it was just a way that it was our technique for generating random packings based on data we already had sitting in the lab. And like I said, we tried some other methods and they gave us very different results. And so that's a study that remains to be done of what that was. Okay, so I started off by saying we were interested in how grains would fail, and we got we went off on this excursion into lattices, and I'm going to come back to lattices again at the end. But I want to return to the original problem, which is how rigidity arises in granular experiments. Okay, so we didn't totally throw out the lovely data we had taken when we turned it into lattices. In fact, this data taken by Jonathan Coulomb when he was in my lab, and then we passed off the analysis of the project to Quang Liu, who's a graduate student at the time. He's now a postdoc with Hermann Moxley. At the time, he was a graduate student with Jen Schwartz, working with Jen Schwartz and Zilke Henkes. And we said, all right, let's look for the origins of rigidity in these granular packings in which we can very clearly see how the forces are being transmitted, and we can also see where all the particles are. Okay, and so we use a lighting scheme that I apologize if you are red-green colorblind. The computer is not red-green colorblind, thankfully, and so we illuminate the particles in green in the polarized channel and in red in the non-polarized channel, so we can use the color separation inside our camera to separately analyze the forces as compared to the particle position. So we can track both of those. Okay, so what comes out of one of these experiments is a list of where all the particles are and who is connected to whom and where they go in the next time step, right? And what the vector contact forces are at each of those particle contacts. Okay, so it's a very rich data set. It is comparable in nature to what one would hope to get from a simulation, okay, with subject to some experimental imperfections that are challenging. But it allowed for the first time for us to start to look at some of the same rigidity percolation and jamming ideas that theorists have been able to do and experimentalists have found extremely challenging to tackle. And so that's the project underway here. Okay, and so now we're going to move away from those network models and add a little more physics in. And this is still a less physics to more physics continuum. So there is the less physics version is that we can do, freshman physics, torque and force balance, right? The technique we use is something called the pebble game that I'll tell you a little bit about in a minute. Okay, but essentially you're looking at constraints, degrees of freedom. This is the same analysis done on truss structures since the 19th century, right? And the question is, for some subregion of your material, are there clusters of particles where you can satisfy all of your degrees of freedom match with your constraints, and you know that that area is rigid. So we can identify that. Okay, so that has some physics, but not a lot of physics, right? It doesn't look at, it's mostly topology and just a little bit of physics thrown in. Okay. The second way we're going to look at things is to consider the vibrational modes, right? So now this isn't totally kosher for a dissipative system, right? So a dissipative system we have both from friction and from elasticity, but you can linearize the interactions around the center of like an energy well, and you can then go looking for regions which have low frequency modes, and therefore you know they are soft, okay, and floppier than the regions around them. Okay, so we can divide, we can partition our system into low frequency regions and high frequency regions. Okay, and so both of these methods, are means of adapting them to experimental data and making assumptions about how we and approximations to do that. This is actually, the paper is just out this week, and the supplemental material is where all of the description of how we do these approximations is written up. And so it's some techniques that Zilka and Henges and Jen Schwartz have used before. But if you're interested in the details, this is now an extremely detailed description. Okay, so the technique we're going to use for constraints counting is something called the pebble game. So basically the aim is, so starting from step 1 on the left, you have some packing. You look at the normal and tangential forces and you decide, is that a contact that is frictionally blocked or is it sliding? So it's a Coulomb failure criteria at each contact. Okay, and so these are classified orange or blue depending on which they are. Okay, and then the pebble game is basically was developed by Mike Thorpe. It's like a bit like playing Go or Chinese checkers. You put pebbles in spots on the board. You have a set of rules, right? And you can they're set up so that if you follow this algorithm, okay, and you need to make sure that you cover every degree of freedom with a constraint, okay? And if you do that, then you will discover that after you've moved all your pebbles around trying to cover your degrees of freedom with constraints, you will discover that here, this green region is a spot where you were able, in fact, to do that, and the part that does not have green was a place that you were unable to solve that problem. So this is a computational technique that allows you to uncover where those rigid clusters are. Okay, so we can do that on our data. The second thing we can do is, looking at the energy viewpoint of things, is to look at some examples of our packings. Okay, and A, B, C, D correspond to the same pictures on the left and right. These are just some examples. And once you have go looking for what the eigenvalues of a dynamical matrix are, what you can see is there's very clearly a low frequency population and a high frequency population. You can draw a threshold between there. What we then do as the rest of our analysis is not terribly sensitive to this threshold. And so everything that's purple, okay, is what we are, in the left-hand picture is what we're calling rigid, okay? And these are for different values of Z, right? And not surprisingly, as you have a larger connectivity, it gets more and more rigid. Okay, so these are our two techniques, okay? And we can look and we can compare them. So here's a comparison between them. So the force chains are on the left, okay, and I've put some red arrows so you can see which side is squished in and which side is squished out. So this is under shear. And the vibrational technique, which has much more physics in it, is what's shown in the middle. Okay, that's the purple is the regions that we are declaring rigid because they have high frequency modes. And if you look on the right in what's labeled D here, those are the areas that were declared rigid by the pebble game. And there is a high degree of overlap between these. Okay, and so you can do a statistical analysis called an adjusted rand index, and it scores very, very well on that metric. Okay, so yeah.
I think there's a question. There's a hand raised.
Okay, I can't see those. Sorry, someone should just ask it. Yeah.
Hi, Karen. This is Mahesh.
Hi.
How do you obtain the vibrational modes in the event that you are perturbing your system? Your frictional, the tangential stresses would start relaxing, wouldn't they?
Right. So we aren't actually perturbing our system, right? So this is so we are saying for a static system. So when it's in this, say, state C, right, we're calling that a static system, right? Now imagine that it had a minute perturbation, right? What would be the vibrational modes of that state? You're correct that this could likely cause a failure, right? And that is not something that we consider, right? This is only saying that if you just linearize around that state, what would the vibrational modes be? Not that that state is a valid state or a stable state or anything beyond that.
Thank you so much.
Yeah. Okay. So if we do that, right, we get that these are just in this one snapshot in a high degree of agreement. But what's, I mean, almost more fascinating to me is if you look at the picture at the left, which is, you know, the pictures that I look at, you know, every day of my life, you know, for a long time now. And, you know, some of you who know me say I'm always going on and on about how wonderful force chains are. I challenge you to look at B and decide what C and D would look like. You know, there are plenty of strong force chains in B that do not show up in C and D. Okay, so I think this is incredibly interesting just at this snapshot here. So if we look at the patterns of the force chains, those tell you that you've got a state that satisfies locally on each particle torque and force balance at a stable configuration, right? A particle satisfies Newton's laws, great, okay. But it doesn't tell you about the stability, the rigidity of that system. It just says, this is the force on me right now. Okay. So both of these other two methods involve a calculation that is not local. It's not just your particle being in torque and force balance. It's a collaboration of you and the other particles in your environment, okay, that lead to that determination. Okay, and what it ends up being is that there are some force chains that are, while they are quite strong, okay, are not actually part of a rigid region. Okay, and they may well be floppy. Okay, you're not going to be surprised to hear me say, I'm going to wonder, those are the ones that are about to break. I don't know the answer to that question. Okay, we will get there again. Okay, but I think it's very important to note that just looking at the force chains, who's strong and who's weak, as lots of us have been doing, doesn't tell you how rigid that area is. Okay, you actually have to do a more detailed calculation. And, you know, I don't pretend that these calculations are perfect, right? You know, we made significant, Mahesh just pointed one out, significant approximations go into arriving at these, okay? And so in some sense, because different approximations and assumptions and things we ignored, decisions were made differently for C than for D, and yet they arrived at a very similar structure, gives credence to these as having some physical reality. All right, so I'll show you a movie now as it goes through the steps. Okay, so you'll see the force chains on the left, the raw force chain image, and you'll see as we shear the system, clusters, oops, the word vibrational and constraint should be swapped. That's backwards. The purple is the vibrational and the multicolor is the constraints. Apologize for that. Okay. And you can see the underlying force chain structure in dark gray. You can see that at all stages, there's even at very low connectivity, right? As the clusters start to form, often they're initiated by the walls, okay? There's always a high degree of correspondence between these two pictures, okay, in all cases. So at all Z's, at all steps, for all samples that we ran, okay? A very high degree of correlation. Okay, so instead of a movie now, here's just a scatter plot. So if what fraction of the sample of the material, so I'm calling them shear and unshear. So shear is going one direction and unshear is coming back. So you see that these are in a high degree of correspondence. If we measure them with the rigid clusters is with the pebble game, rigid regions is with the vibrational modes, and they're in a high degree of agreement, you know, at all time steps. It's slightly off of linear, but very close. We also can figure out what the threshold for global rigidity is, right? So if we define that as being that we have a 50-50 probability of finding a system spanning cluster over all of our examples, and importantly, we do not toss out any rattlers here. Every particle that's in the system is in the system, okay? And I think this is really important because a particle these are, again, like I said, it's not just a local calculation about that particle. When we're calculating, you know, the rigid clusters, any particle that's in contact can be contributing to stabilizing that cluster. And so you can't, in the next time step, it may be needed, right? So no rattlers are tossed out. This is truly the Z for the system, as best we can determine it from experiments, okay? And we find that the threshold for the global rigidity is, and this is using the pebble game analysis, is about Z is 2.4. Okay, so this is below Z equals 3. Okay, and as such, it sure seems like maybe these mesoscale structures, okay, are what's controlling it. Okay, these are things that are not just system-wide averages. They're very specific to the structure that you have. Okay, and that seems to be what's controlling the global rigidity. Okay. We of course can do clusters where we either include the rattlers or we don't. And we can look at how the pressure is different inside the rigid clusters and not. And we're running out of time, so I'm going to spend just a very brief moment on this and say that yes, the pressure inside the rigid clusters, that's in blue on the right, is larger than the pressure outside the clusters, right? So it's not that the force chains are useless. Okay, there are actually more force chains inside the rigid clusters. That's what's causing them to be rigid. Okay, but any particular force chain, that's less obviously true of. Okay, we also can characterize the floppy region. For those of us who have succumbed to the pandemic hobby of baking sourdough bread, here's an example of my own on the right. You know, not everything that has holes has problems. You know, having holes is prized in sourdough bread. We have similar floppy holes in our packings. And so what's been highlighted in this picture are the characteristics of those floppy regions, okay? And everything inside one of those floppy regions are particles that are not contributing to the global stability, okay? So there's huge chunks of it that are not participating, and yet they're part of the material, okay? And they may become important in the next stage of deformation, but they aren't at that moment. Okay. I'm gonna skip some of this to go forward. So, I started off saying I'm interested in where things are going to fail. So are these floppy regions that I found, are they going to be the places that fail? Okay, I don't know. This is another question I do not know the answer to because we haven't figured it out yet in the granular materials. But we have started to look at it in the lattices again. So now I'm going to go back to that. And I'm just going to have you guys recall, right, that for low Z, we had ductile-like failure. That's the movie playing at left. And actually this picture is the wrong picture here. On the right, we had brittle-like failure, okay? And now I'm gonna show you what happens if we use that pebble game on this system. Okay, so this is the same set of pictures I showed you before, only of different networks that we borrowed from the granular materials and printed up in acrylics. And we're now gonna play a pebble game on these. And what you're seeing here are those rigid clusters that we got from the pebble game. Okay, and on the left, you can see that there's not many rigid clusters. They're small and they're sparse. As you go towards the right with higher connectivity, you have system spanning rigid clusters, and then in between, you have in between. As statistical physicists, this is not a surprise to us. Okay, so we can consider this as being, the ones on the left are flexible. They're mostly composed of floppy regions. These are things that all those bars can bend and accommodate tremendous amount of displacement. Okay. Everything on the right, where we have rigid cluster percolation, they have very much fewer ways they can accommodate any strain that's imposed. Okay, so left is flexible, corresponds to ductile. Rigid cluster percolation corresponds to brittle. If it fails, it's probably going to cause a cascading failure. Okay, and now I'm going to zoom in on the middle guy. Okay, so in the middle, okay, so this is the one that has Z equals 3, which if it were an infinite friction granular material, which is sort of what one of these lattices are, that would be the transition point. That's the isostatic point where on average, the number of constraints, the number of degrees of freedom matches. Okay, so that's exactly the spot where that is. Seems to be the transition between the ductile behavior and the rigid behavior is right at this spot. And we don't have good error bars on this because of the nature of the way we did the experiments, okay? But it does seem coincidentally close to 3. Okay, you can notice we don't have a 2.9, we don't have a 3.1. We didn't do those experiments. So let's zoom in on that guy and take a look at him. And lo and behold, this is one example, but it's very intriguing. So every place that's an orange circle is a spot where a failure occurred. And it sure looks like those failures are clustered along the floppy regions between the rigid regions. Okay, and so this pebble game analysis, okay, which describes where the rigid regions are, at the same time also tells you the not rigid regions, okay, by elimination. And those seem to be those flexible, those bonds that are more flexible, more able to bend. If you're more able to bend, you can more easily be pushed past the point of failure for the plastic material, and therefore you're the one who breaks. Okay, so being in a rigid cluster actually protects the bond from having too much torsion, too much stretching, right, too much compression, and therefore they don't break. Okay, so this is illustrative of something that may be a broader effect, but for which we do not have good statistics. Okay, so I just want to close with something, is that just a slightly different way to think about what I've just told you that is, what I've been thinking a lot about recently is I feel like, the vibrational picture is about energy, right? And, if that particle, gets enough energy, you can get over a hump into the next energy minima, right? And so there's an energy landscape you might think of in here that we're not probing in this experiment, right? This experiment was done with static steps, okay? But if we take it further, we can see that there's a chain of energy minima that a particle might transition between, okay? That's a different way of thinking about failure than thinking about Coulomb failure, right? So Coulomb failure is if you have, ceased to satisfy your friction threshold, you've exceeded it, then you'll have slip at that point, right? And you will have exceeded the threshold force as opposed to exceeded a threshold energy. Okay, so these are two different ways to think about the problem. And I'm gonna show you a very interesting experiment that we've been working on in the lab. This is some analysis done by a new grad student in my group, Kai-Shin Song. So he's pushing a chain of particles through a little barrier, and the little barriers are named top and bottom. And particle one goes through the gap, then number two, then number three, then number four. And something you can see in this, that's the graph at the bottom as particle numbers 1, 2, 3, and 4 squeeze through. And this is noisy data, but what you can see is there's an energy maximum, a force magnitude. You also think that is energy magnitude, right? It has to squeeze through by compression, okay? And only then later does it fail. So we see elements of both an elastic energy-like behavior and a Coulomb failure behavior. Both of those appear to show up in our data. Okay, and so maybe that is why we're seeing that both of these give very good descriptions for where the rigidity is. All right, so some conclusions. I showed you a couple different viewpoints for looking at disordered materials, ranging from more physics to less physics. Obviously, more physics gives you better predictions and you get better understanding, but really simple models can be surprisingly effective. And we saw in several cases that just the topology was a very, very strong control on the system. And I think that's the big message. The more detailed message is that we're able to do all sorts of cool things like identifying where force chains are more or less likely to be, where failure locations are more or less likely to be, that we can identify rigid regions through multiple methods that are in agreement with each other. And it's really promising that maybe some of the non-rigid areas, what we're calling floppy regions, may be more prone to failures, and at least for some lattices, maybe more generally than that. And the last thing I wanted to say is that huge thanks to all of the folks out in the community, and we're trying to participate this ourselves, who are making their science toolboxes openly available. So if you want to play with our science, we have our data from our papers. We're on Data Dryad. We have published how we did our photoelastic solving to get the forces. Zilka has published how she did the calculations of the pebble game and the rigidity percolation and the vibrational modes. You can get that from her space on GitHub, and all the network analysis we're getting from people in the network science community who give us that. And so huge shout out to all the people who are open to sharing, because that's what's made it possible to do all of the work that I've shown here. Thanks.
All right, thank you so much, Karen. So the floor is open for questions. And actually, I see a hand raised, Kinsey.
Hi, yeah, my name's Tom Kinsey. I do have it's kind of, I guess, a comment on similarities of what you're looking at to some of the stuff that I look at. So block copolymer phase separation with brick and mortar morphologies. There's been some studies where the cavitation is measured after a force is applied, and the rubbery connective regions are the ones that have these voids, these failures, whereas the rigid glassy bricks are the ones that give it more of the structure. And it's just kind of
yeah, no, I mean, I think it's quite likely we see similar stuff. So I'd love if you send me what you're working on. I'd love to know, to read more about it.
Yeah,
but
I will.
How
for
do you
sure.
So how do you know where is rigid and where isn't? I mean,
So the different blocks, so block copolymers, one, you have a glassy block and a rubbery block, and then they phase separate. And depending on the architecture of the polymer, you can get these discrete glassy regions with very thin rubbery mortar-like regions.
So I guess my question is far simpler. Do you tell by looking at them or by poking?
So yeah, it's a macroscopic deformation with scattering at specific locations.
Okay, so you can see them. You can see
and then you're measuring the cavitations.
That's cool, because you can see that. We can't see that. We cannot see where the rigid and floppies are unless we do a fair bit of work.
Right, but
so that's
what
cool.
You're seeing is
probably the same thing. Yeah.
Those fractures are between the rigid regions and the more floppy regions. So.
Yeah. But our materials are the same in both places, right? That's what's sort of weird.
That's
right?
true, yeah.
Yeah, it's so that the material is the same. It's the configuration of the material that's causing the problem.
Interesting. Well, thank you. This was great. Thank you.
Thanks for that.
Can I ask something, please?
Sure, dive in.
Okay, I have a couple of questions. First of all, it's great working, very interesting. One question is super naive and the other is very naive. So I will start from super naive. So you seem to suggest that your intuition is that failure should probably happen in floppy regions, while my intuition would be just the opposite, that floppy regions are flexible and you don't fail. I'm thinking that catastrophic failures of our bodies happen when we break some bones, not break muscles. So what am I misunderstanding here?
I don't know, actually, because so I agree with what you say. And I also have our observations, right? So to some extent, I'm trying to understand how to explain what we observe. But I think I can explain it a little bit. So the floppy regions have the same material as the rigid regions, right? And I think this gets to Kinsey's question, comment as well. They're the same. They're literally the same material. So it's not like bone and muscle, which are made of different material. But what's different is some of I'll go with talking about the lattices here, since that's where we've observed it, right? So some of the edges and nodes of the lattice are embedded in a rigid space where, because everything around them is rigid, they're not going to be subjected to large deformations, right? Compared to something that's surrounded by a region that's floppy, where the very floppiness of the region will then cause more bending, right? Cause more torsion, right? Than it would have if it was in a rigid region. So this is not the conventional way to think about them. And I think it's because the material is the same and they're subject to two different deformations because they're in two different environments. But this is me talking conceptually about an observation. I have not tested what I'm saying.
I understand. So the idea that these floppy regions, they floppy until they deform too much and then they fail rapidly. So it's like initial curve is very shallow, and then it goes very rapidly up.
Well, yeah, so depending on what you mean by up or down. So the force loads and then it drops off quickly. So it's the same way most things, I would say, operate. But you're right. It does not fit with the bone versus muscle. It does not fit with the tree versus grass, right? Aesop's fable, right? I'm saying something that sort of runs counter to how we usually think about this.
I guess I was trying to think about your floppy and solid regions as composite material, as floppy region is like muscle and solid region is like bone. But
I think that's the key distinction. I think this pairs really nicely with Kinsey just said, is that what's different here, it's the material is the same, it's the environment that's different. And I think that's not how I have ever thought about it before.
If I may, I have another question. This is what you're collecting samples with different average Z by looking at the movie and taking movie in the different places. That is sort of, as I understand it, the way to generate a random configuration. But when you take random configurations, there are two sorts of randomness. One sort of randomness is how your particles are positioned. And this is something that you see more or less. And another one is this roughness of the surface, and this is something that you don't see at all, how these surfaces are touching one another. My question is it possible to, in order to control better the second type of roughness, the second type of randomness, is it possible to intentionally make these surfaces more rough? It's difficult to make them less rough, but it's probably possible to make.
Right. So with the grain, you're talking now with the grains, yeah. So funny you should ask that. We actually, so there are, so folks from Bob Behringer's group have cast gear-shaped particles that have a huge degree of roughness. Okay. So that limit has been explored. You can sort of get to the infinite friction or close to infinite friction limit. Actually, we are mucking around with this right now as we speak. So playing around with fabrication techniques that will allow us to get particles with roughness that we decide upon rather than what we get by the manufacturing process. So right now, the roughness we get is what the manufacturing process gives us. And if we can get some 3D printing techniques to work on appropriate materials, we might be able to move past that. But I don't have that working, but it's definitely something we're thinking about.
Thank you.
Yeah.
So I have a question that might be not answerable, which is how different is 3D? And I got fixated on this because I was trying to imagine what three-dimensional Mancala would look like along the lines of three-dimensional Star Trek chess games. Are there avenues to understanding 3D packings?
So my understanding is that the 3D version of the Pebble game is problematic. And I'm not going to speak to the details of that, but I think that is known to be a challenge. For me, the challenge is looking at things in vibrational modes I don't see as a problem. For me, the challenge is we have very few techniques for seeing the forces inside 3 dimensions, right? So here is where I really love the fact that the network techniques work quite well, is that the idea of doing 3D experiments, and yes, Ryan Hurley's work with using a combination of X-ray diffraction, X-ray tomography to extract forces. I mean, there are people who can do this, right? It is so difficult and you don't get large data sets, right? If we could get tools working that only required that you make good guesses about things being in contact, right? That opens up everyone who does confocal microscopy, right? Huge swaths of people can now start to use some of this, right? That couldn't before in 3D. And I agree that 3D is the more interesting and more important case, right? And so
I didn't say that. I just wanted.
I know you did, but I'm fully cognizant that I'm cheating by working in 2D. But I do think that if we can understand how to do things with just the networks, that's really, really powerful. And I will say that we did a little bit of this when we were trying to predict where the force chains were going to go using Betweenness Centrality. We basically, one thing you can do is make your data worse than it is. You can't make it better than it is, but you can make your data worse, right? And so we played with the idea of like, what if we don't know who's in contact? We just guess who's in contact, say, yeah, 10% of the radius, good enough for me. It still largely works, right? So some of these things were really robust to us crapifying our data, right? So I think these are really promising for those of you who have 3D data and you don't know what the forces are. You know, I mean, Yasna does in emulsions, right? But this is really, really quite rare for people to have access to that information. And it's a pain to get it, right? That's the other thing.
So we're just waiting to see if there's a last question creeping in. And if I don't see it, which I don't yet, let us thank Karen one more time for a super seminar. And I will stop the recording and we can all just hang out afterwards.